What I want to do now was take you through some of the basic ideas of neural networks and deep learning and so on. I realized that for some of you, I was chatting with a few people, some of you have, I think there's a very diverse set of backgrounds in this room. Some of you know a bit about machine learning, but are relatively new to deep learning. Others of you in this room have already published papers in deep learning, so there's a wide range of backgrounds. For those of you that are more advanced, I think some of this, what I'm going to do in the next hour or two, is going to seem relatively basic, but hopefully it'll also give you some new perspectives on even understanding stuff that you already know. And then I promise towards the end of today, I'll get to some more advanced things again as well, that even those of you that are writing research papers on deep learning, I think there'll be stuff that's new to you. Okay, but what I want to do for the next couple bits was start from the basics, I guess, so that some of this will complement stuff that Jan was doing yesterday on the kind of intro to deep learning. But I want to make sure that when you go away, end of today, you have a deeper actual understanding of the album's work rather than the high level, ooh, it all seems cool to me type impression. Okay? So, in two pieces, I want to spend some time talking about neural network representations and what is the neural network and how do you implement it and what do neural networks compute. And it turns out neural networks are a great way for us to learn nonlinear hypotheses, right? So, given a training set like this one, let me see if this works. Right, and so given a training set like this one, if you want to learn a decision boundary that distinguishes the positive and the negative examples, right? Neural network would be a great way to do this. One way to do this would be to hand code nonlinear features and then train a linear classifier. But we've seen for problems like object recognition, right? We don't really know what nonlinear features to choose. So if you look at your positive and negative examples of detecting cars versus motorcycles, if you look at your positive and negative examples where you have positive and negative examples like that, often we don't really know, well, we have a hard time choosing features. And so what we're going to do is just let the learning algorithm sort out what nonlinearities we want in the function in order to learn to recognize objects. Okay? So, all right. So let's start by talking about the model representation and maybe the high-level loose inspiration for the field of neural networks, right? So I think the field of neural networks had its origins in kind of algorithms that try to mimic the brain, and neural nets were very widely used in the 80s and early 90s, and many of you know that popularity diminished in the 90s when machine learning moved towards convex optimization methods like support vector machines and so on, and I think part of it was that throughout the 80s and 90s we didn't really have the computational power in order to train the highly nonlinear, non-convex, very complicated things that neural networks are. But I feel like more recently, through deep learning and so on, deep learning is maybe the new rebranding, I guess, of neural networks, because it's a cool sounding name. But I think recently we've all seen a major resurgence in neural networks and is now a state-of-the-art technique for many problems. So, how does the brain work, right? Your brain and mine is jam-packed full of neurons, like the one shown here. And neural networks were loosely inspired as building rough simulations of these neurons, right? So many people have been using neural networks without really knowing, where some of the ideas came from. So I thought it'd be fun to show you. So that's your neuron, and that's the nucleus, right? And the dendrites of a neuron are, if you will, the input wires to the neuron. And depending on what inputs your neuron gets, here in the neuron's cell body, it'll do some computation, and depending on the result of that computation, it may decide whether or not to send an electrical pulse, or like a spike, down this output wire, like so. right? And these output wires are then connected to other neurons, which may in turn, takes as input the output of this neuron, do their own computation, and decide whether or not to send additional electrical signals onto other neurons, right? And this is how all of human thought, human motion, and so on work, is these neurons generating signals with maybe one neuron here sending pulses of electricity to a different neuron. This neuron may decide to send pulses of electricity maybe to a muscle, and that causes your arm to move, or may send pulses of electricity to other neurons, and this is the stuff of which thought and of which human thinking is made of, right? So the simple, maybe almost brain-dead simulation of a neuron is a simple logistic unit, right? So this is a maybe incredibly simple, vastly oversimplistic, I should say, model, computer simulation of a neuron. And what this model neuron does is it inputs 3 row numbers, x1, x2, x3. And the way we draw these neural networks very often will also have draw it with what's called a bias unit. So we just draw a +1 that also feeds in there. So the +1 is called a bias unit. And what this little neuron does is it does the computation and outputs the value h of x, which is given by h of x equals 1 over 1 plus e to the negative theta transpose x, okay? Where here, x is a vector with x0, x1, x2, x3, where x0, I guess, is alternative notation for my bias unit +1, and theta is my vector parameters, theta 0, theta 1, theta 2, theta 3, okay? So all that this little neuron does is it takes the inner product between x and theta, and it applies equals 1 over 1 plus e to the negative z, which is called the logistic function or the sigmoid function to it. And that's my little simulation of a neuron, okay? Actually, how many of you know what a sigmoid function looks like? Okay, cool. All right, essentially almost everyone. No, all right, I'll just skip it. Great. So that's my simulation of a single neuron. And when we put a bunch of these together, you get a neural network, right? Where we have, I guess, a number of inputs here, a number of hidden units here, and an output node over there. And so just to step through this neural network a little bit, right? This is what the computation represented by this neural network is. So let's use some different colors. So that node there, I wrote as a superscript 2 subscript 1. Don't worry about the notation, it's not important. But that node there performs this computation. It takes, this sort of inner product between the inputs x and part of my feature, my parameter matrix, and applies a sigmoid function to that. And then my second hidden unit, shown in green, applies the sigmoid function to a different linear combination of the inputs. And then my third hidden unit here, outputs a value A3, which is given by that. And finally, my output unit, shown in cyan, right, looks at the values computed in the previous layer. So looks at this, looks at these activations computed in the previous layer. Sorry about the mess on the slide. And computes a linear function of that and applies a sigmoid function, and that's the final output of the neural network, okay? When you're implementing, as I mentioned, one implementational trick, I guess, that when you're implementing neural networks, these things take a long time to train. When you learn to implement neural networks in MATLAB or Python or even C++ Java, there's one trick that you should be aware of, which is called vectorization. I'm just going to describe it at a very high level here, and then if you want to see the full details, I don't know, look through the tutorial on the website or something. Instead of writing extensive for loops all over the place in order to do these computations, if you can express these things in terms of vector operations, then often the code will run much faster, because in all major languages, including C++, Java, but definitely MATLAB, Python, NumPy, there are numerical linear algebra libraries that will help you to implement these algorithms that can do linear algebra operations much more quickly than you could possibly implement yourself using for loops. So here's what I mean. Instead of, well, let me just write this out, I guess. If you look at what this computation is doing, right? That block of computations is basically doing this step, right? Z2 equals theta 1 and matrix times x, right? And so, sorry about the confusing notation, but so this quantity that I'm circling in green, the first element of the vector z, that's exactly equal to this quantity that I'm circling. And in a similar vein, this second quantity that I'm circling in blue, that's exactly equal to this thing in blue, and similarly for the third element, okay? So what this means is that when you're implementing a neural network, instead of writing for loops to do all these multiplications yourself, what you should do is find a good numerical linear algebra library and use your numerical linear algebra library to take the matrix theta and tell it to multiply that by the vector x. And this will be far more efficient than something that you could write yourself, because it'll take advantage of instruction level parallelism, that's built inside the processor, like SIMD instructions and so on. And then, anyway, and similarly, if you're doing this in MATLAB, I tend to use MATLAB and Octave. If you have a vector implementation G that takes this input, G of an input Z1, Z2, Z3 that applies the sigmoid function element-wise to these things, then again, that's another way to get a much faster, much more efficient implementation than if you're doing these things yourself. One way I like to think about a neural network is that, so there are different ways of thinking about what neural networks do. One way I like to think about it is that a neural network is an algorithm that can learn its own features. So here's what I mean. Let me take this neural network. I'm going to cover up the left half of it, right? And so each of those yellow circles represents like a logistic regression algorithm, right? It's basically logistic regression. So if you look at what this neural network is doing, it's saying that, h of x is logistic regression applied to the features A1, A2, A3, right? So what the neural network is doing is exactly saying that, let's say I have some set of features, A1, A2, A3, with which to represent my data. The way that I'm going to recognize, cars versus motorcycle, whatever computer vision task I want to solve, is I'm going to run logistic regression on my three features, A1, A2, A3, and that's how I'm going to predict cars versus motorcycles. Right? That's exactly what this is doing. And the cool thing about a neural network is that instead of needing you to code up the features by yourself, it learns those three features, A1, A2, A3, automatically, right? So, and then obviously as well, there are sort of other network architectures that that one can use. So I guess this is the basics of what a neural network how a neural network representation works. What I'd like to do next is step through some examples and intuitions of these neural network architectures and of why they can represent complex functions. Before I do that, let me ask you, I think on the handout, for those of you that have been doing this will be incredibly basic, but I think you should know enough to do questions 9 and 10. And these two are just a little bit more tricky, I guess. So if you're one of the people that's more advanced, if you see if there's anyone less advanced than you and can help them out with these, that would be useful as well. Yeah, all right. So I guess first question, I guess the answers, it's kind of complicated to write out, but hopefully you're all writing something like that. You know, the first A21 is like a sigmoid function of W1 times 1 plus W2 times x1 and so on. And then the final output is, you know, h of x is sigmoid of some, W5 plus W6, you know. Something like that, right? If you're not sure if you got this right, I suspect most of you got this right, and check with your neighbor or something. Question 10, what did you guys get? N plus 1 whole thing squared, right? I think I did this last night. I think that's what I got to. Oh, sorry, no, wait. Oh, no, sorry. Wait, what's the answer again? Someone tell me the right answer. So nm plus m. Okay, cool. Does that seem right? So I guess if the first layer has n units plus a hidden unit, that's n plus 1. Oh, n plus 1. And then if the hidden layer has n plus 1, and then the output layer has 1, so this would be, between the input layer and the hidden layer would be n plus 1 times n, then between the output layer will be n plus 1 times 1. And so what is that? Mn plus plus 1. Yeah, okay, cool. Something like that. Does this seem right? Okay, all right, cool. Great. Awesome. Okay, cool. So let me quickly step through, you know, an example of why neural networks can represent highly nonlinear functions. You know, here's an example of a nonlinear classification problem, right? Which is you want to learn the XOR or the XNOR function. Suppose you have inputs x1 and x2, which are binary values. X1 and x2 are either 0 or 1. And if and the exclusive OR function says, you know, is one of them 1 and one of them 0. So the training set looks like the one shown on the shown in the figure, where the x's are positive examples and the o's are negative examples. So, and in order to, you know, kind of just make some of this easier to think about, I'm gonna just spread out the examples, right? So imagine you have a training set like that shown on the right, you know, can you have an algorithm that can automatically learn a decision boundary, right? That is a nonlinear decision boundary that separates the positive and negative examples like that. So let's see. What I plotted up here is the XOR function, right? Exclusive OR. But what I'd like to work this example using is actually the XNOR example. That's the negation of the XOR example. So it's just the negative, right? The XNOR means not X1 XOR X2. And the XNOR function just makes the rest of this a little bit easier to do, okay? So let's start with the basics. Can we come up with a neural network to compute the AND function? And it turns out that by choosing appropriate weights for this network, you can do so. So first, you know, so we have two inputs which are binary valued, and let me add in the bias unit plus 1 as well. And what I'm going to do is I'm going to draw the weights on the little arrows of this network. Let's say I'm going to choose weights with the following values. The weight from the bias unit to the output node, let's say I set that as minus 30. From x1 to the output node, I'm going to choose that weight as plus 20. And then from x2 to the output node, I'm going to choose a weight of plus 20. Okay? So now my single neuron neural network is going to compute h of x equals sigmoid function times negative 30 times 1 plus 20x1 plus 20x2, right? And so if we throw in what this looks like, so I guess just as a reminder, I guess, you know, the sigmoid function looks like this, right? If it's z on the horizontal axis. So if the input is 0, 0, then we end up computing g of negative 30, and so, you know, it's like negative 30 is out here, which is very close to 0. If the input is 0, 1, then that's g of negative 30 plus 20 plus 0, so that's g of minus 10, which is also approximately equal to 0. If it's 1, 0, g of minus 10 is approximately 0. And g of 1, 1, that's the only case where you have minus 30 plus 20 plus 20, so you have g of 10, which is approximately 1, right? Since, I don't know, just this is 10 out here. And so if you look in this column on the right, what this means is that h of x, you know, is approximately x1 and x2, right? Because with this little single neural network, the output is 1 if and only if x1 and x2 are both 1. Okay, so this is a simple example of a neural network being able to compute like a simple logical function. One more quick example. So you can also write a neural network that computes an OR function, right? So I've written out, you know, the weights on this neural network, and so it's going to compute the function g of z equals minus, h of x equals g of minus 10 plus 20x1 plus 20x2. And so if x1, x2 are both equal to 0, this is going to be g of minus 10. And so that's approximately 0. 0, 1, this gives g of 10, which is approximately 1, approximately 1. And so this network computes h of x is approximately x1 logical OR of x2. So we talked about how to get a network to compute, you know, x1 and x2, and to compute x1 or x2. Why don't you do an example? So this is the next question on the handout. Can you choose weights? You know, choose 2 weight values, one for that parameter, one for that parameter, so that this computes the negation function. All right, so here's what I had. This is what I had. It's 10 on top and minus 20 at the bottom. So if x1 is 0, so let's see. So this is computing, therefore, that function. So if x1 is 0, right, then this gives you g of 10, which is approximately 1. Whereas if x1 is 1, then this is 10 minus 20, so you have g of minus 10, which is approximately 0. And so it turns out that, I guess, to compute negations, you know, usually, I guess, the trick ends up being to have these negative weights associated with a node, and that ends up being the negation. Okay. And so going back to our original example, you know, earlier on we talked about how to come up with a network that computes x1 and x2. We also talked about a network that computes this, x1 or x2. And then something I didn't talk about, but you can take my word for it, you know, you can also have a network that computes this not x1 and not x2. And it turns out that by putting these together, you can then, you know, compute the x-nor function that we talked about earlier, right? And this will require, so you can't learn a nonlinear function with just one hidden unit, with just a single neuron, because this logistic regression is just a linear classifier. But by stacking together a few of these different neurons, you can now compute a nonlinear function. So let me fill this in. So I'm going to take the red network and copy that over here, right, with weights equal to minus 30, 20, 20. And this node I'm going to call, I guess, A2 subscript 1. And then I'm going to take the blue network, the one that was in the middle, and put that over here with weights equal to 10 minus 20 minus 20. And I'm going to call this node A2, 2. Right, so that's this node. That was that one. And then finally, I'm going to take these two, add a +1 bias unit, and hook these up to the green network with weights given by minus 10, 20, 20. And then it's finally this green network that outputs, the result of my hypothesis. Okay? So you remember the red network was computing the AND function. So let's fill in the truth table. When x1, x2 are both 0, the AND of that is 0, 0, 1, and so on. So that's what the red neuron outputs. The blue neuron computes not x1 and not x2. And so it turns out if you fill that out, you get the following truth table. And finally, the green network takes the OR of these two pairs of values, and so you end up with the following truth table, right? And thus that kind of illustrates how this particular network is able to represent the XOR, the XNOR function. And I think this is the challenge and excitement, I guess, behind deep learning. I think the term deep learning refers to the idea of learning networks with multiple layers of representation. And the XOR function was an example of a function that we cannot represent unless we have at least one hidden layer. And more generally, as we have neural networks with multiple hidden layers, you can imagine building up more and more and more complex functions by adding additional layers to the network. The challenge, of course, is that with a multiple layered network like this, the learning problem becomes non-convex, and so you need both appropriate algorithms as well as sufficient data and sufficient computational power in order to train the parameters of a deep network like this one. So let me actually finish off the discussion on representation by showing you, when I teach my machine learning class at Stanford, I always use Jan's video to illustrate this notion of what the multiple layers of representation are computing. So, if you look at a network like this, right, you have input pixels, and the question is, what is the second layer computing? What is the third layer computing? I mean, what is the network doing on this final way to generating the output? So in this video, when I play it, let's see. So in this video, when I play it, this region shows the input to the network. And this first column over here is a visualization of what the first hidden layer is computing. So it's a visualization of the source of edges or whatever it is that the first hidden layer of the network is doing. And then the second and third hidden layers are a little bit harder to visualize and understand. But that's the visualization of the next hidden layer. That's the visualization of the next hidden layer. And I guess this shown there is the final output of the neural network, right? Oh, I should have said, this is a work that I guess Jan had done back in the, 80s, early 90s. And in the history of neural networks, one of the early huge success stories of machine learning was reading zip codes. It was one of the things that allows you to send, US mail like across the country for, 43 cents, 44 cents, or whatever it costs now, right? I think back in the late 80s, early 90s, there was a huge push to automate sending of US mail to bring down the cost of the US mail service. And the ability to read zip codes was a large part of that. You probably don't know this, but today when you send US mail, when you handwrite out the address, software algorithms actually read not just the zip code, but the rest of the address as well. It's, from like, I don't know, 123 Stonehenge Road or whatever. It actually reads the entire thing that you read, that you write using OCR. But I think it has its early beginnings in just starting to read the zip code to help route mail along. And so this is one of the attempts to use machine learning to do that. And it's still, and this zip code stuff is still considered one of the major success stories of machine learning from the 90s. All right, but let me show you this fun video. And as you watch the video, you can see the source of inputs fed to the algorithm, as well as the source of things computed by the hidden units and what the neural network outputs. Oh, is you playing the music? Oh, wow. So next time you send US mail, feel free to do that. All right. So using neural networks for, so talked about neural networks for binary classification. So let me say a little bit about how to use it for multi-class classification. There are many ways to do this, but let's say you want to design a neural network to distinguish between 4 object classes: pedestrians, cars, motorcycles, and trucks. So instead of having one output unit, what you can do is then have multiple output units, have 4 output units, where for each of the 4 classes, we're going to associate a target vector. So for the first class, we're going to arbitrarily associate it with the first basis vector. For the second class, we're going to arbitrarily associate it with the basis vector 0, 1, 0, 0, and so on, right? So that we try to get the neural network to output this when it's a pedestrian, output this when it's a car, output one with the third position was a motorcycle, and so on. And then we hopefully get the neural network with 4 output units to output 4 bits with a 1 in the correct position, depending on what object class is detected in the image. And so this is also called the this is sometimes also called the 1 versus all encoding, where in the training set also you would encode your target value y as one of these 4 basis vectors, and then you train the neural network to output 4 bits to be close to what's observed in the training set. And then at test time, when you run your neural network will output 4 real values, and then you predict whichever one of the 4 real values has the highest activation. Okay, so that wraps up what I want to say about neural network representations. I'm tempted to, let's say, the next piece I want to do was go on to talk about learning. So we talked about what the neural network can represent, and the next piece that I want to talk about is, now that we know if we were to go in and hand set all these real numbers, we can represent complex functions like the XOR function and more complex functions. The next question is, how do you automatically learn the parameters of the neural network? So maybe because this is a natural break, let's just break early now, and then when we come back, talk about how to use neural networks for supervised learning, how to use it for unsupervised feature learning, as well as pre-training, fine-tuning, and start to get into, I'll spend some more time on the basics so that everyone is up to speed on the basics. But in the next, let's break a little early, and then in the next block of time, we'll get a little bit further into the actual details of how to do deep learning and unsupervised feature learning and self-taught learning using these algorithms.